My learners, I am Ankur Dhiman. Welcome back to my channel. I am excited to kick off a brand new video series on machine element design. Each week, we will dive deep into the design process of one machine element, breaking it down step by step. So, if you have ever felt stuck while designing shafts, this video is for you. Today, I will guide you through the complete shaft design process in a clear, structured way. Stay tuned and don't forget to subscribe so you don't miss the upcoming episodes. So, let's quickly jumping down to shaft design for industrial application. First consideration is layout. The general layout of a shaft to accommodate shaft elements, for example, gears, bearings, and pulleys, must be specified early in the design process in order to perform a free body force analysis and to obtain shear moment diagrams. The geometry of a shaft is generally that of a stepped cylinder. The use of shaft shoulder is an excellent means of axially locating the shaft elements and to carry any thrust loads. Figure 1 shows an example of a stepped shaft supporting the two pulleys. It is supported by pulley 1, pulley 2, and this in green color, in blue color is the shaft, and these cross portions 1 and 2nd is here. These are bearings and the spacings are given. So this type of layout you will have to plan in first phase of designing a shaft. Now moving to the next phase, which is pick the material. A good practice is to start with an inexpensive low or medium carbon steel for the first time through the design calculations. If strength considerations turn out to dominate over deflections, then a higher strength material should be tried, allowing the shaft sizes to be reduced until excess deflection becomes an issue. The cost of the material and its processing must be weighted against the need for smaller shaft diameters. Now moving to the next phase, which is calculate stresses. It is not necessary to evaluate the stresses in a shaft at every point. A few potentially critical locations will suffice. Critical locations will usually be on the outer surface, at axial locations, where the bending moment is large, where the torque is present, and where stress concentrations exist. By direct comparisons of various points along the shaft, a few critical locations can be identified upon which to base the design. An assessment of typical stress situation will help. We will have to find out which section is critical by drawing the bending moment and shear force diagram for the shaft. As you can see in the adjacent figure, the critical point will be in the middle of the shaft because the bending moment will be maximum on these locations. Now going to the next phase, which is check deflections. Deflection analysis at even a single point of interest requires a complete geometry information of the entire shaft. For this reason, it is desirable to design the dimensions at critical locations to handle the stresses and fill in reasonable estimates for all other dimensions. Before performing a deflection analysis, deflection of shaft, both linear and angular, should be checked at gears and bearings. Allowable deflections will depend on many factors, and bearing and gear catalogs should be used for guidance on available misalignment for specific bearings and gears. Coming to the next phase, verify vibration limit. When a shaft is turning, essentially causes a centrifugal force deflection, which is resisted by the shaft's flexural rigidity EI. As long as deflections are very small, no harm is done. Another potential problem, however, is called critical speed. At critical speeds, the shaft is unstable, with deflections increasing without upper bound. It is fortunate that although the dynamic deflection shape is unknown, using a static deflection curve gives an excellent estimate of the lowest critical speed. Such a curve meets the boundary condition of the differential equation, zero moment and deflection at both bearings. And the shaft energy is not particularly sensitive to the exact shape of the deflection curve. Designers seek first critical speed at least twice the operating speed. That wraps up our discussion on the shaft design. Remember, the process involves 5 key steps, and it is important to revisit and refine your results if they don't meet expectations. I will stop here for today, but in the next video I will cover the mathematical formulas involved in this video, but I will walk you through a practical example to make the process even more clearer. I hope you find this helpful. If you did, don't forget to like, share and subscribe. See you in the next one. Thank you.